Okay, so just as we talk about isomers here, this is a bit of a summary on the isomers. I have questions all the time about positional, structural, geometric, and optical isomers. So here's a bit of an explanation. Positional isomers were the first one we talked about, and a positional isomer is where the placement of a double bond would change. So if we had a double bond being placed in the first bond position like this, and versus the same number of carbons in a chain with the double bond being in a different position, these would be positional isomers, okay? Positional isomers, the position of the double bond. A structural isomer is where carbons are attached to different carbons. So here we have a 1, 2, 3, 4, 5. We have 5 carbons in the longest chain that we can make. Here we have 1, 2, 3, 4 carbons in the longest chain that we can make, because one of these carbons is not attached to the end anymore. It's attached to one of the carbons that would be in the middle. So this is a structural. Okay, so we've got positional, that's the double bond. We've got structural, and this is where carbons are attached to different carbons. Structural. And you think about a structure, a building, how it's put together, right? How it's sort of built and attached. The third type of isomer that we talked about was a geometric isomer, geometric, and that is that's referring to the arrangements around a double bond. So you think about the cis and the trans; those are geometric, slightly different than the structural. This is specifically arrangements around a double bond, the geometric isomers. The geometry, if you think about the geometry, sort of, when I think of geometry, I think of parallel, perpendicular, I think of angles and things. So think about the sort of the angles of the groups, right? What angles are they on? Either, same side of the double bond or stretching geometrically on opposite sides, cis, trans. That's geometric. And then finally, optical is the fourth type. We actually talked about this one maybe first, I don't know. But the optical isomers are where you have mirror images, okay? So groups, compounds are in mirror images of each other. And the best way that I think that you should consider this is count kind of in some kind of logical order, A, then B, then C, then D. And if you can go all the way around in a circle like this, just make sure that you cross the carbon in this counting for an optical isomer at least once. So here, instead of from A going to the left or the right, okay, to get to B, you have to go across the C to get to B. That's definitely an optical isomer. And that's how you would draw that two-dimensionally. So just make sure you don't go around in a circle with the isomer that you draw. So this one goes from A across the C to B. See? A, B, and then C, and then D. So something like that. Okay? I think you also could draw it like this, where you have A, and then if you go to B, you have to go then across to C and D. So I think that's also going to work. You have to cross the carbon at some point. Was there a question there? Yep. So if this is not including A, B, and C, so if I give you this, okay, would this be an isomer? Okay, would this be an isomer if I drew it like this? Okay, is that an optical isomer, yes or no? I heard a yes. Yeah, okay, I'm hearing yeses and nos.
It goes opposite.
No, because the NH2 is after the side.
So if I started NH the same way as I did up here, okay, so here I obviously went to the ethyl group here. So NH to the ethyl group. Can I still get to the ethyl group without crossing a C? Yes. From the ethyl group, can I get to the OH without crossing a C? Yes. Can I get to the last one? Yes. So this is not an optical isomer. Not. The answer is no there. If you traded just one of these, this is OH, CH3. Now, if you count the same as what you did from NH2, okay, I have to go, can I get to CH2? Yeah, the ethyl. Okay, I can get to the ethyl right there. Okay. From the ethyl now, can I get to the OH without crossing over the C? No. So I have to go across the C here. Okay? And so this is an optical isomer, yes. So I'm not going to, probably on a test, you're not going to get a nice A, B, C, D. You know, here you go. It's probably going to be something like this, and you'll have to give me an optical isomer. So I guess just going back here to isomers, the definition of an isomer, they have the same formula, okay? Same formula, but there's something different about their arrangement, something different about the structure, okay? Or the arrangement of things, of atoms or bonds. Different structure or arrangement. Okay? So that's, I should have mentioned that first, but I think that, I guess the understanding was that you knew what an isomer was, it's just the difference between these two. So yeah, if I give you a molecule or a structure and I say give me a positional isomer of this, then you'd have to move the double bond somewhere. If I asked for a structural isomer, you would have to actually pick up, remove a carbon, put it somewhere else, and so on. Yeah. Okay, so that's the summary of the isomers.